Hello everyone, welcome to Kepler. Today we will be discussing the problems for the contest Codeforces round 1067. So let us jump into the problem. For the first problem, we are given that a game is initially being played with n players, and basically in the game the referee can give a red card and yellow cards, and the player gets knocked out if the player receives a red card or two yellow cards. So we are given the total number of red and yellow cards combined in the match. So we will use a greedy approach for this. So given number of red cards and yellow cards, we can just give all the yellow cards just to separate candidates. That means each player gets two yellow cards. So at most one y by 2 number of players get knocked out with yellow card, and plus separate number of red card players get knocked out. So and we ensure that this is less than n because the number of players is n, so this has to be less than equal to n. So we ensure that it's minimum of n. So this is the formula for getting the number of players who will be knocked out, and this is just a simple, you just write this to get the answer. So again, for the code, it is very simple, as you can see. Y by 2 players get knocked out with a yellow card, and R players get knocked out with a red card. Great. So now for the next problem. Yeah. So for the next problem, we are given a sequence of 2n integers, and f of b denotes the number of distinct elements with an odd frequency. So to find two distinct frequencies p and q of size n, each of size n, such that f of p plus f of q is minimized, and the original array of length of the original array is 2n. Right. So let's take an example. Say if it's take this one 3376 3787. So seven, 8, 7. So one way to distribute this to ensure maximum occurrences or maximum f values, 3, 3, 3, 3, then 7, then 6. This is one part, and another part is 3, 7, 7, 8. Right. 6. Yeah. So for this part, f of p is the 3 occurs 2 times, so it will be counted. 7 and 6 occur 1 time, so odd frequency, so these two will be counted. So f of p is 2, and f of q is also 7 won't be counted because 7 occurs 2 times. 3 and 8 is counted because it occurs an odd number of times, it is 1 time, so 2. So our answer becomes 4. So let's make some observations on this. Firstly, suppose in the original array, the frequency of one of the elements ai is suppose is odd, right? Now, if we try to split this into two different parts, say v1 instances go to p, and v2 instances go to q. Now, since v1 plus v2 since v1 plus v2 is odd, both these cannot be odd, right? Because odd plus odd becomes even. So at least one is even. So basically, either the point will go to p or q, depending on which either v1 or v2 is odd. So in this case, our net increase in the answer is +1. Now what happens in case of, say, just a minute. Yeah. Yeah. So what happens if, let's say, uh, if f of ai is, well, let's call this frequency, right? If frequency of a of I is odd. So if it is odd, then on net increment the score is 1 because either p is getting the odd value or q is getting the odd value. Now what happens is if frequency of a of I is even, right? In this case, if we split it into v1 and v2 parts for p and q, either it's odd and odd or even and even. Now obviously we'll always have to make it odd because in this case we will get plus 2 points for both these parts p and q. So basically 1 part for p and 1 part for q. In this case it's plus 0 because neither part gets the point. So this is always the optimal case we would like to go for. Now suppose let's say we have something like 5577. So in this case we'll get assign the 2 5s to 2 different parts and 2 7s to 2 different parts. So our final split is 5/7 and 5/7, which is plus for 4. Okay. So in general, if frequency of a of I by 2 is odd, we can just split 5 5 and 7 7. Like we will split the number between two different parts in an odd manner to get a score 2 times. But what happens if frequency by 2 is even? So it gets a bit tricky here. Like how do we handle this edge case? Because in this case we cannot split into two halves because of something like 5 5 5 5. Even if we split into two halves, we are left with 2 5s on this side and 2 5s on in through. So neither part get a point. So this is not optimal split. Right. So if you look at the samples we had, yeah, for example, this one 2 2 2 2. The answer is 0 because for example here we cannot do it split it like this, even though in this case both become odd. Two splits become non-equal in size. It is given that the size must be equal to n, right? So we cannot split it in a non-even manner. So what can we do in this case? So suppose we have something like this 4 4 4 4 and 7 7 7 7. One thing we can do here is put 1 4 in P and 3 4s in Q. Similarly, 3 7s in P and 1 7 in Q. So now it is perfectly optimized since we are getting both scores out of 4 out of 7, and the odd counts here are for both cases are odd for both 4 and 7. So in general, so we know that like if our frequency of I by 2 is odd, what we'll do is suppose you have two different elements like this, so frequency of let's say another element has such that frequency of j by 2 is also odd. These are two different ing elements. So what we can do is frequency of, for one part we give frequency of pi by 2 minus 1 and frequency of I by 2 plus 1. So basically we are giving one of the parts one less element and one part more. So this makes both this odd. And for the j part, we do it the inverse. So we can give by 2 plus 1, we give p more and q less. So this is just a generalization of what we did here. Basically, splitting this both in an uneven way and distributing them so that both p and q end up with the same number of elements. So if you do that, we can have maintain an equal size for both p and q, and also ensure that the frequency remains odd for both these numbers. Now there's just one final edge case. Even if we have only one kind of this frequency by I by 2 odd element, we can still manage to distribute it properly. There's one more edge case, which is what is 1, 1.3, 1. It's clear. So if you look back on the edge cases, like on the samples we had, I think it was this one. So 4 4s here. Wait, and distribute them. So some splits we can do here is let's say okay, so it should be 1 2 3 4. So 1 2 3 4, and if we have another say 1, this is 4 4, and okay, yeah. So if it was something like 4 4 4 and then 1 7, we can make it like this: 4 1 7 and 4 4 4. So instead of distributing the odds evenly in both the p and q, we put the odd or like original odd elements in the same to make it equal. And also the number of odd elements, like the number of odd occurrence elements will always be even, because we know that the size of the entire array is even of 2n. So we have some even elements, like some even frequency elements and some odd frequency elements. So for this part to be even, the number of odd frequency elements must be even also. So we'll always have some even frequency elements, and so in that case, if we have it, we can just use these odd frequency element to deal with this type of blocks like this. So let's go just one by one over everything we cover through the code itself. So firstly, we go through each element, and we have three different cases. Firstly, if the frequency is odd, we are including odd count. Otherwise, in case of even, there are two different cases. Firstly, if f by 2 is even, then even count 1. Otherwise, even count 2. Otherwise, even count 1. If in case that f by 2 is odd. Now, if f by 2 is even, odd, like I discussed, you can just split it in 2 and share it into a p and q. So this is just even count 1 into 2. And really for odd count, I mentioned that only one part can get a share of that odd count of the odd frequency element. So we only add this just once. And for the even count 2 elements, as I mentioned, if there are multiple even count 2 elements, we can pair them up to distribute them effectively. Otherwise, we can use the odd count elements to distribute them. So for the edge case, like for example, just 4 4 4 6. In this case, there is no way to split them. So in this case, answer is 0. So for this edge case, we will instate that if there is this even count 2 type of element remaining, and there are no odd count elements left, then we will decrement this, because this cannot be split. So once we have that, we can just use this formula to find the final answer. Great. So let's look at problem C now. Problem C is given that we have two arrays A and B, and we can perform k different types of operations, For each operation, we can increment ai by bi or decrement ai by bi. And Alice and Bob will play a game with this type of move for k turns. And at the end of the k turn, our goal is that Alice's goal is to maximize the sub-array sum, and Bob's goal is to minimize the sub-array sum. So let's take an example. Say, let's take this one. C1 2 minus 7 3. So for problem C, one of the sample cases was C1 2 minus 7 3, and I think it was 1 11 3. Right. So one possible way to optimize this was to Alice will perform one operation on this cliff, change this to 4 3, and so the final the maximum subaddition sum is this entire thing, 2 plus 4 plus 3, which is 9. Yeah. So there are actually only two, in the case of the game Alice and Bob are playing, there are only two cases. Let's suppose the optimal move Alice can make is say AK, incrementing AK plus BI, and suppose after this move, the subarray A of L2R becomes maximum. Right now, if the number of K is if number of moves is even, which means that after each of Alice's move, Bob will also get a move. So what I mean is both Alice and Bob get an equal number of moves. So every time Alice increments AK by BI, Bob will also decrement AK by BI, because we know that this is the most optimal possible increment in this in the current array. So regardless of if Bob decrements any other element, uh, it will always be less than decrementing it by BI. So for example, if I use this example, say 1 1 1, and then let's say 1 2 1, yeah. So suppose Alice increments it by plus 2 here, so it becomes 3 now. Now if Bob decrements this by let's say decrements this by this one, so this becomes 1 3 0. In this case the favorization is plus 4, right? But if Bob had decremented this instead, it would have become 1 1 1 plus 3. So the Bob's optimal operation always to just reverse Alice's move. So both the players will try to increment and decrement this maximum BI value all the time. So if K is even, then essentially there is no net change in the array, because all the increments and decrements get cancelled out. So in that case, the answer is just a normal maximum subarray sum on the final array. This can be just calculated using Cartan's algorithm. Right. If K is even, then the answer is just maximum of L comma A of L2. But what happens is if K is odd, in this case we have Alice can leave increment Vi to the array, so the final array becomes something different, and now we have to find a maximum subarray sum of this. So the answer will now become maximum of some AI, some Bi which Alice is incrementing, and on this new array A of L to R plus Bi, where I lies in this range L to R. So basically we're incrementing I and finding the maximum range between this maximum subarray sum, such that the element I is included in this subarray. So now our problem becomes finding this entire thing. Suppose we manually check. Let's say Alice makes a move on a random BI set. Let's say Alice increments BI. In this case, what is the maximum subarray which includes I? If you think about subarray in terms of prefix sums, the sum of A of L to R is nothing but prefix of R minus prefix of L minus. So if we want L and R to be to contain this index I, we need to find the maximum prefix from I to n. So the maximum prefix value and the minimum prefix value on the left hand pointer. So minimum of I no 0 to I minus 1 prefix of L. So we have almost sort of deformulated the entire equation. So basically our formula to find out the maximum subarray sum containing a given index I. So this is very easy to do. We just compute the prefix sum first for the entire array A. Next, next we take the this is the suffix maximum, and this is the prefix minimum. So we can either perform another array which stores this suffix maximum and prefix minimum of this prefix array fixed sum array. So using this, we can find out for each index I what is the best subarray in order of quantile, and so basically check through every single BI and find the best possible sum for this BI. So the overall complexity becomes order of n. So let's look at the code for a bit. Yeah. So we calculate the prefix sum. Then I have used a sparse table. Sparse table is basically a data structure which can use to calculate the range-wise maximum minimum, but you can also use the prefix and suffix minimum maximum like I discussed before. And then once we have this, firstly we take the maximum prefix from I to n, then the minimum prefix from 0 to n, and we subtract this to get the maximum subarray sum containing the index I. And if k is odd like I discussed, then we have a additional bi left over, so we add bi to this. Okay, so now let's move to problem D. So D is quite interesting. It is given that we have two binary strings S and T, and what we can do is we can pick a palindrome from S, which is whose length is greater than 1, and flip all the bits in this palindrome. So for example, for this problem 0 1 0 and 1 1 1, zero 0 1 0 1 1 1, and what was the second part? 1 0 0 0. So one possible solution for this is to firstly apply this operation on this part 1 2 3. So switch from 0 0 0 1 1. Next we apply it on this part. This gives us the okay, no. Okay, so this will be different. We apply it on this part 0 1 0. We get 1 0 1 1 1 1, and then again on this part we get 1 0 0 0 0. Yeah. So this is one possible way to get the operation. So I will first propose a sort of greedy approach, or a kind of greedy idea. It is not entirely perfect, but I will explain how we will remove the imperfections later. But let us first consider a greedy idea. If we start move from left to right and say S of I is not equal to T of I, if S of I is equal to S of I plus 1, right? In that case, because this in that case I and I plus 1 for palindrome, so we can perform this an operation I plus 1 to change Si to Ti. Otherwise, suppose S of I and S of I plus 1 are not equal. If S of I is equal to S of I plus 2, right? In that case, we perform the operation on I to I plus 2. Because you can say something like this 0 1 0. In this case, I and I plus 1 are not equal, but I and I plus 2 are equal. So we can perform the operation on I and I to I plus 2. Otherwise, suppose if this also does not hold, so something like 0 1 1, we will perform two operations in this case. Firstly, apply to the I plus 1 and I plus 2 to get 0 0 0, and then on the entire thing from I to I plus 2 to get 1 1 1. So effectively this bit get flipped in two moves. So if S of I else firstly I plus 1 and I plus 2, and then I to I comma I plus 2, these two operations. Also it is given that the maximum number of operations we can do is 2 into n. So it would seem that we have found a good solution since we are just performing at most 2 operations for each index. But obviously there are some very obvious edge cases for this. So for example, something like is 1 1 0, and then let's say 1 1 1. Yeah. So in this case, the last bit is changed. So obviously, if we use a given logic, we were only leveraging the elements after S of I. So this would work in this case. Similarly, something like 1 0 1 and 1 1 1. This also does not work with the logic because I and I plus 1 are not equal, and there is no I plus 2 element. This is the second last element. So what do we do to deal with this sort of scenarios? So if you think about a brute force approach to this question, right? So for example, we can use something like a BFS approach or backtracking approach, where suppose we have let's say like this, like for 1 1 0, let's say we have something like this. So one operation we can do is take the entire 1 1 and convert this to this. Then what we can do is 0 1 1 and then 0, or we can take these first two zeros to get 1 1 0, or the last three or the entire thing to get 1 1 1. So a sort of backtracking approach where we brute force through every possible palindrome, convert the string, and then again recheck the entire string. So why I'm saying this is if a string was very small, say something like n equal to 6, then we could have just brute forced this algorithm for this, and it would pass because 2 to the power 6 equal to 64, which is obviously not very time consuming. So what I've done is basically for this problem is this sort of imperfect greedy idea. I have applied it from 0 to n minus 6, right? Now for the remaining part, n minus say 5 to n minus 1, So for 1 to n minus 6, I apply the greedy idea to easily flip all the bits from left to right. Then for the last 6 elements, I apply the BFS approach. Or the backtracking approach they mentioned. So this way, we kind of sort out the first few elements, and for the large edge cases where we have cases like this or this, we use a BFS approach to quickly find out which a possible sequence of operations to get a target or a target string. So let's give you a quick glimpse of how you can implement this BFS. Firstly, you have a visitor array for each string, right? Indicating with data as visitor array, and also a parent array. The parent is basically from what string we have visited this string. For example, parent of 000 is 110, and parent of 111 is 000. And also previous move. So what move you apply to come from the parent to the child. So for example, here we apply the move 1, 2 to get from here to here. Similarly, 1, 3 to get from here to here. So once we have this, we can just sort of backtrack away from the target array to get all the moves we want. So let's look at the code for a bit more clarity. So firstly, for the first n minus 6 element, we just iterate and apply the greedy idea I mentioned. So if I and I plus 1 is equal, we flip this 2. Otherwise, if I and I plus 2 is equal, we flip the 3 elements. Otherwise, we do the 2 move operation I mentioned. Now, once this is done, our first few n minus 6 elements are sorted. So for the last 6 elements, what we do is we apply a brute force approach I mentioned, where I have the visitor array and I also have this previous parent string and parent operation, like the operation I used to move from parent to child. So using this, I apply a breadth first search on the current prefix or current suffix I have, the last 6 elements to reach the last 6 elements in the target array, target string. So you can view this code later to get a better idea, but it's not too hard. And once we have, if we have found, you check if you have found all the found the target suffix, we calculate all the operations to reach this target from the current suffix and print them. Otherwise, we print -1. So obviously, I feel that there might be some other intended solution for this, because for the problem we're given like pretty good legal like order of n square complexity, but I managed to do this much faster, like around order of n plus 64. Like, but let me know what if you guys have another approach, like a much more neater approach than this, because I feel like maybe this approach is not as elegant or like as good. So let me know what you guys think about, or if you have any more ideas on how you can solve this problem. But that's all for today. I hope you enjoyed the problems, my explanations. Do comment and like on this video if you like the explanation, and also make sure to visit the Kepler website for the notes for this video and also other resources. So that's all for today. Thank you.